enough jibber jabber. Let's start taking out some screws, and I will start with the circuit board and its really old school looking connector right here. All the screws are out. Let's flip it over and see what we got. That capacitor is getting in the way. Oh, some of the spacers just fell down there. And there we can see how it's all put together. We got the really nice traces on the bottom of the circuit board, most likely hand laid out with the red plastic tape that would be laid out, and then optical methods would be used to do the etching. But what I'm really interested in is the connector down here, and it seems like it's a whole bunch of clips holding this piece of fiberglass on here. Hopefully I can get it off without breaking it. There we go. So that's it. Really old school and fully customizable edge connector right here. You can see there's all these individual slots in the fiberglass for putting different connectors, different clips anywhere you want to in those slots. Very, very interesting. Never seen anything like this before. And there's all the edge connections, of course, on the circuit board itself. And then we also got some charring here from a resistor right there mounted on the top. And of course, these two screws are for these two big power resistors standing upright. We've got a 20 watt, looking at the print down here, there's a 20 watt resistor as this one, and that's a 15 watt. Now they wouldn't actually be heated up to those powers. 20 watt, this one might be 10 watt, that one might be 5 watt actual power being dissipated in these resistors. But again, that's peanuts compared to the heat emitted from all the tubes too. Each one of these tubes would be getting just as hot as those resistors. There's all these black plastic capacitors standing up. We've got Aerovox Auto Pass written on the side of all of these things. 0.22 microfarad and 600 volt for this one. I don't know what kind of dielectric is in there. Is it wax paper or something else? If anybody knows, please let me know. And this is as far as I'm going to go with the circuit board. I'm not going to take the tubes out or anything. I like it just as it is. I have a keen eye for artistic value in electronic circuits, so at some point I'll probably nail this thing to a wall and just enjoy how nice it looks. Some nice, good 1968 electronic engineering here. Now I should get all these other tubes out of here before I continue with big metal chunks flying around. And these big octal socket tubes, they're held in place with these little metal grippers down here. And sometimes it can be a real bitch to push down these springy metal leads, and they even have little metal teeth on there on the edge. You can just about see the metal teeth, and they really get a good grip on the base. You can see the marks that they leave here on the base, but hey, that holds the tube in place, so this thing can get jostled around quite a bit, and these tubes are not going to fall out. And I noticed that both of these RCA rectifier tubes are missing the plastic key on the bottom that's supposed to be surrounding the evacuation tube of the glass right there. It's supposed to look like this little cylinder protruding from the base with a notch on the one side to make sure you get the pins all in the right position. These are completely broken off here. Someone at some point in time was not very careful in removing these tubes. It may also be a design flaw. I mean, it's possible that this brown plastic at some point in some manufacturing process must have been accidentally been made exceptionally brittle, and that might be a reason why it happened. Or maybe someone was just very, very careless in removing these tubes. However, someone was careful to make sure that they do get inserted in the right place, because there's these two marks right here, just black permanent marker on the side, and on the bases there's a black permanent marker right there, and also right here on the right next to the screw and going onto the chassis, there's a little mark right there. So that's how you can tell that these tubes are put in place if all those black marks line up. And as for that 6AS7 that was between the two rectifier tubes, you can see it's quite dirty inside there. That might be a reason for that little bit of purplish glow from a little bit of gas that might be inside there. The getter material still seems intact. It's still all silvery color up here on the glass envelope. Maybe these little specks are just from the mica wafer that holds all the plate materials in place. I don't know. I mean, it could be completely benign, or it may actually have an effect on the operation of the tube. So that leaves us with just one more tube at the front of the unit. Here's the tube socket for this tube, which I took out already. It's the 6AF3 high voltage rectifier tube, and I was looking at the tube and its location in the circuit and the schematic, and also looking at this thick wire on here, thick insulated wire, and comparing it to some of the thinner insulated wire on here. And that got me thinking, there must be a lot of voltage on this thing. Now I know it can generate up to 600 volts on the beam output and 900 volts on the reflector output, but this wire looks like it can handle much more than that. So that got me digging a little deeper to see what really is capable total output voltage from this thing. Now here's a look at that tube in the schematic. It's this one right here, V106, and it basically goes up here to the negative reflector output. And I read the text in the manual, and it says that it's here to prevent any kind of positive bias on this reflector, because this is always supposed to have a negative voltage. You never want a positive voltage on the reflector, because then electrons will be attracted to it. You don't want that. You want those electrons to be bouncing off of that. So then I drew up a very simple diagram of a klystron and the two voltages going to it. And right now is a good time for me to bring out a real klystron. I forgot that I had this thing, otherwise I would have shown it in the first video. Raytheon RK5976. I couldn't find any specific data sheet for this, but it is very similar in construction and pin out to 2K25, which is a very, very common klystron, and I'll include a data sheet for that in the description. Anyway, on the bottom here we've got pins 1, 2, 4, 7, and 8. Now 2 and 7 are the filament pins right there, filament connections. Number 8 is for the cathode, and number 1 is for the resonator, which also happens to be the entire case of the thing too, as well as the coaxial shield on the RF output, which is right here in place where pin 4 normally would be on a normal tube. There's also a cap on top. That's for a connection to the reflector plate in there. And you'll see these two posts right here on the side. This one is just stationary, that doesn't move, but this one over here has a screw with threads going in opposite directions on either end of the screw. So if you turn it one way, then these two metal plates, they splay apart and basically pull the top cylinder down a little bit closer, a little bit harder onto the main body, and that changes the shape of the resonator ever so slightly. It doesn't have to change much in order to change the frequency. And in fact, here's that 2K25 data sheet, and you can see that the range is only 8.5 to 9.6 gigahertz. So not a wide range, but still very tunable depending on the location, on the position of this special screw that's in here. And if you turn the screw the other way, then these two reeds, they come closer together and push that thing up to widen the resonator a little bit, to make it a little bit larger. The resonator itself is just a tiny little pancake section at the top of the main body right here. Now let's have a look at the voltages being applied to this Klystron tube right here. This particular power supply has the two outputs that are both isolated, or at least isolated from ground. So you can put up to 600 volts on the beam voltage and 900 volts on the reflector voltage. And by the way, if you actually do that on a 2K25 or even this one, the RK5976, you'd probably destroy it, because the 2K25 at least is rated for 300 volt resonator or beam voltage and 200 volt on the reflector. But regardless, let's assume that this Klystron can handle these voltages, and like I said, everything can potentially be floating until you get to the RF output, and that coaxial shield is most likely going to be grounded, which means that the whole case of this metal tube is going to be grounded, and the pin 1, which is connection to the resonator, is also going to be grounded, which means that the positive output of your beam voltage is going to be ground, the same chassis ground that this thing is. So that means you've got negative 600 volts on the cathode, and then up to negative 1500 volts on the reflector with respect to ground. Negative 1500 volts potentially on one or multiple of these wires in here and other components. You can have up to 1500 volts difference with respect to the chassis ground. So really potentially dangerous stuff. And that's why many of the wires in this thing have such thick insulation, because of the potential for 1500 volt difference between the wire and the chassis ground. Finally, now with all the tubes removed, we can really start to dig into this thing. I'm going to start by taking all the knobs and pots off of the front panel here, and we can also clip all the nylon zip ties on all the wires in here. You can see that they really went to town with the zip ties on all these wiring bundles here. They must have been assembled on a wiring harness, of course, all the individual wires cut to length and then wrapped around pegs on a big piece of wood, and then all zip tied according to manufacturing spec. Very nicely done. Okay, I have removed everything from the front panel except this one BNC connector, which is a pain to get to from behind. So let me flip it open. There we go. What a nice collection of wires and pots and switches and zip ties. And on the rear of the front panel is July 15th, 1968 stamped on there. So again, this thing is definitely made 1968, about 47 years old now. There's a whole view at the front panel. And by the way, this thing is steel. The outside frame is aluminum, but the front panel plate is made of steel. It's no wonder this thing was so freaking heavy. I never actually weighed it, but it's spec'd at 38 pounds. And also this magnet came from the front analog meter that was right in here. Here's all the other pieces. So I just took that thing apart really for the magnet. I can add the magnet to my collection. I don't need the meter at all. I've got plenty of other analog meters. Here's a closer look at some of those pots from the front panel. We've got this ginormous 100 kilo ohm pot that was the control for the reflector voltage. And so I think there's a lot of stuff going on here. We'll take a look at that at the end of the video. There's two other pots here that are interesting, and I'll talk about them, with these plastic spacers on the shafts. And they are not here for physical constraints, space constraints or anything like that to get them away from the front panel. They're actually here for electrical isolation. So you can see that this is just completely plastic all up along the length of this this collar here, except for the end of it. That's metal hardware for mounting it, of course. And then we've got some metal hardware on the end of this plastic shaft right here, and so that basically completely isolates this from the front panel, of course, for safety concerns. Now, normally in a regular pot like this, the shaft is isolated anyway from the electrical portions in there, from the wiper and from the resistance going around there between the terminals. It normally is isolated anyway, but apparently some extra special precautions were needed for these two pots. These are for the modulation amplitude and the modulation frequency right here. We can see them in the schematic. So right there, there's the dual ganged pot for the modulation amplitude, and this one right up here for modulation frequency. Now, I don't know exactly what voltage is on these things, but obviously it's got to be a lot for the designers to see the need to have the extra electrical isolation here. And you can see some of that thick wire on here. So, and even on this one, every single terminal has the thick insulated wire. This one has thick insulated wire on the one end of it and thinner wire on the other end of it. So possibly low voltage here and high voltage here, and of course the wiper could go anywhere from low to high voltage, and so that's why they would need this extra electrical isolation on this thing. Okay, fast forward an hour and a half, and we've got the chassis completely emptied off here. Everything taken off except for these little plastic screw holes here for the top circuit board that was in place, and everything else is completely removed. Now, this whole thing is steel, as well as the front panel, of course, and the outside casing was also steel. So I'll be collecting all that and adding it to the steel scrap pile, take it to a scrap yard one of these days. Some more things that'll be going to a scrap yard are these transformers. I've got plenty of transformers from vacuum tube equipment that I've taken apart over the years, and I really don't need any more. Plus, it will be a real pain in the ass to keep track of all the different terminals on here and the voltages and the current. And that's another thing, I don't have any current ratings on any of the coils in here. I did Google the manufacturer and the part number on here for both of these transformers, and I couldn't find anything. So these will be hitting the scrap yard as well. And also this little dinky shaded pole fan motor. I've got a whole bunch of these already, and I don't need another one. So that's gonna end up in the scrap bin too. And one more little bit of scrap is all this copper wire right here. Yeah, just insulated copper wire. Be getting rid of that. And by the way, all this stuff was held together with, I counted it, 104 nylon zip ties. Some things to be going into the trash, of course, are this wafer switch. This was for the modulation mode selection, and a little connector here for the output of the whole power supply. Now let's have a look at the things I'll be keeping, and that includes these capacitors, the oil capacitors that were inside this thing. We've got 4 of these 4 microfarad 1200 volt each. These big ones here, as well as a little dinky one here, 0.1 microfarad 1500 volt DC, and half a microfarad 600 volt DC. I'll probably get rid of this one. I mean, it's really not worth holding on to that. But all these higher voltage caps, they might come in handy for some high voltage experiments or high voltage power supply that I might want to build later on. This one had a little hook on it like that, or a holder, keep it onto the chassis. These other guys, they had these metal strip hooks on here to basically clip on the bottom of the cap, which in the chassis would hold the capacitor onto the chassis, onto the metal plate in there, and of course there would be a couple holes in the chassis for the two terminals. But that's how these things got held in. So I'll be keeping these things as well. If I hold on to the caps, got to hold on to the mounting hardware too. And this one too had its own little baby hooks to hold that thing in place as well. As for tube sockets, I don't really need any more tube sockets. I wasn't planning on taking these things off in the first place until I decided that I wanted to keep these little tube base grabber doohickey thingies. So I took these off. I want to keep these in case I want to make my own tube circuit from scratch. And if I want to ruggedize it, these would certainly come in handy. But as for these, I'll just toss them in the box with all the other tube sockets. That's why I didn't even bother unsoldering the wires from here. So, because they might never get used, they might end up in the trash at some point in time. I have no idea. But hey, whatever. I'll just keep them for now and see what becomes of them. The small metal wheel on the bottom of the chassis. Couple of fuse sockets. Some high voltage insulated pots. This is actually a couple of 10K pots on here. This is a 1 meg, and this one is spec'd at 0.25 meg ohm, if you can see it at some point there. And we've got a wafer switch. So this one is, I don't know, I just kept it. It's a lot easier, simpler than the other 3-layer wafer switch that was in there. This one was for the voltmeter and ammeter selection, so maybe that'll come in handy at some point, at some decade maybe. And toggle switch, double pole, single throw, and this 604 kilo ohm resistor, 1% tolerance. That was for the voltmeter. And of course we got 5 knobs to add to my big box of knob collection. Or possibly 6 knobs, because now we're going to have a closer look, as promised, at this reflector voltage pot. 100K. Let's have a look at the label right here. So 2% tolerance, 100 kilo ohms, and type M301 from Samarius Incorporated. Alright, so that's all I can decode from this thing. You even have a date of 5/6/8, so maybe that's May of 1968. I'm not entirely certain, but I'm going to have a look at this mechanism right here, and also pop off some screws and have a look on the inside of the pot too. And here's an exploded view. Use an Allen wrench to get the knob off of the shaft of the mechanism right here, and of course there's the dial, which was held on by a couple of screws onto the mechanism as well. The middle part right there, that's the shaft, and then there's this outer ring right here. That's what the dial was screwed onto. And then of course this thing has a hole down here, and that has a couple of set screws in there, flathead set screws, flathead screwdriver, and that goes straight onto the pot. And this pot actually has some kind of plastic non-metallic shaft going through the middle of it. Now the way this thing works is that you can see if I turn it just a whole bunch, turn that shaft several turns, then this part of it, the other brass cylinder here, only turns 1 turn for, actually I've counted 6.5 turns of the shaft. I gotta turn that shaft 6.5 times in order to get this thing to turn just once, and this is also attached to the washer up here onto which the dial was screwed on. So the dial and the pot shaft, those are both coupled together, and I have that shown right in here on this picture. So here's a cross section looking straight down onto it like there. There's the shaft, and it actually has 4 ball bearings inside there. The shaft contacts these ball bearings, and the other side of the ball bearings contacts this outer steel casing, and then the pot and the dial are both attached to the brass cylinder which goes in between the shaft and the casing. So as the balls move in between the shaft and the casing, then so follows the pot and the dial. This kind of mechanism was used quite often back then in old equipment such as this, in order to get some extra precision when turning pots. And if you didn't want to have the great expense of using a multi-turn pot that actually had a really long resistance wrapped around in a helical coil in there, just a regular 300-degree potentiometer, you could use that and get a lot of extra precision by having a mechanism like this, where you just turn the knob a whole bunch and the wiper inside only turns a little bit. And took off that bottom panel. Here's the inside of the pot in all of its wire wound glory. So yeah, it's just a big strip of phenolic material in there with wire wrapped around it, resistance wire of course, and then that strip itself is wrapped around on the inside with the break in between the two ends of it right there in the middle. So a lot of actual distance here. Seems like only like 10 degrees of no connection right there on the wiper, and then we've got another 350 degrees all the way around. The center tap connection is made with these 2 springy wires right here that, and put that back in place, they dig down into this brass pulley, I guess you could call it, and of course that goes to the wiper pins spooling around on the inside there. Really nice, really awesome construction. This is actually 100 kilo ohm resistor, 100 kilo ohm pot. You don't really see wire wound pots with such high resistance. Usually they're 100 ohms or less for wire wound pots. To get one that like this, that's 100 kilo ohm, very high quality and very nice. So I got that pot back together now. One other thing I'll be keeping is the highly inefficient indicator lamp. Look at that. Tiny little red lens that the light shines through, and then it just goes everywhere else. And then of course there's the circuit board, the vacuum tube circuit board from the top. Like I said, I was going to put it on a wall as a decoration, and there it is. And of course the fan blade from the cooling fan that was inside that thing. And we've got this the keypad from the Nokia cell phone that I just took apart a few weeks ago. And this thing from a few months ago, this was the main circuit board from a computer tape drive that I did a teardown video on that as well, and a couple other things. I don't even remember where these things came from, but hey, it's very pretty stuff in my opinion. So thanks for watching. If you learned something in this video, or this pair of videos of this teardown of the Klystron power supply, then please give it a thumbs up. See you later.